Hello everyone, I'm J Wildberger. Thanks for joining me. We're looking at diffusion symmetry, and today we're going to be talking about something of great interest to chemists. We'll look at lattices in 2D, so-called Bravais lattices, and looking at them from both a group theory point of view, in other words, a traditional point of view, but also moving towards a hypergroup understanding of them. And a good place to start is with a very explicit example, which is that of the square lattice, okay, whose associated point group is a very important finite group called D4. This is the dihedral group, otherwise known as symmetries of the square. It's arguably the second most important finite group after S3. And the elucidation of its characters and the class and character hypergroups, I think, will be really useful for us. Okay, and it will also have lots of applications to chemistry and physics. Okay, so we're talking now about crystals, okay, motivated by actual physical, chemical things where you have these regular patterns of atoms that create these structures with all kinds of beautiful face-like structures. And it all comes down to the configuration of the atoms in a very regular pattern. And the regularity is expressed, first of all, by a translation kind of symmetry, so that this thing is sort of uniform across the space, but also there is sort of local and additional symmetries. So the chemists have studied these things for quite a long time. In the early 1800s, a chemist physicist called Bravais sort of classified these the different kinds of lattices up to sort of Euclidean transformations like rotations, reflections, scalings. And in 2D, the situation is quite simple, relatively simple, but still not entirely trivial. There are 4 2D crystal families, and they are the oblique lattice, rectangular lattice, the hexagonal lattice, and the square lattice. And we're going to be concentrating on the square lattice, but let's have a look at, first of all, at these 4 interesting families. So the oblique lattice starts out by basically having a parallelogram. So you have a separation here and a separation here, which is not 90 degrees. And it's also not a rhombus, so that this separation here is different from this separation here. And there's a regularity, so we go an equal amount in these directions, we go an equal amount in these directions, and we end up with this 2-dimensional lattice. Now, in all cases, I'm just representing a finite portion of the lattice, okay? But we should imagine that these patterns carry on in all 4 directions. Okay, so that's an oblique lattice. And this little green parallelogram there is a unit cell, so that the entire plane can be thought of as being covered by translates of this thing. The rectangular lattice, well, as the name suggests, it's built up from a rectangular unit cell, and the sides are perpendicular, but these separations here are not the same. The hexagonal lattice is familiar if you're packing coins in the plane. That forms a very pleasant pattern where if you put a coin here, then it's touching exactly 6 neighboring coins. So this is a hexagonal lattice, and its unit cell is looking like this, with a 60 degrees or 1/6 of a turn there. And then the most regular lattice, perhaps, is that of the square lattice, which is like a rectangular lattice, except that now we're talking about a square in the middle as the unit cell. And it has a regularity in all directions. And this is the most familiar because this is really just what you see when you look at a piece of graph paper. Now, associated to these 4 crystal families, there are 5 Bravais lattices. So one can consider more subtle objects. So there's a 5th Bravais lattice, which is not on here, which is a kind of a cousin or another one in this rectangular family. So let me just copy that thing again. Here's the rectangular lattice, something like this. And I'll mark out that unit cell there. Okay. Now to get this variant lattice, what we do is we center a new node at the center of all of these little unit cells. So we put nodes like this, and the pattern repeats. So this is another lattice which has the same group theoretical symmetries as does this one, but sort of lattice theoretically it's actually different. So there's actually two kinds here of these rectangular lattices, and that's why we get in total 5 Bravais lattices. So all of these are interesting objects that have a lot of interesting group theory associated to them, and they are very important in chemistry and in physics. But we're going to concentrate on the square lattice because it has a lot of symmetry and because it's arguably the simplest and the most familiar. So let's have a look at the symmetries of the square lattice. Here is the square lattice, and I remind you that it actually goes on in all directions. The symmetries of the square lattice have been studied by different groups of people, and it actually has different names. So the crystallographers often refer to this symmetry group as P4M. Coxeter notation, Coxeter was a very prominent 20th century geometer, is sort of bracket 4, comma 4. And this is orbifold notation, which was introduced by Conway to describe sort of a prior approach to symmetry groups initiated by Macbeth and Thurston. So at some later points, we'll maybe make contact with some of those things. Okay, so how do we describe the symmetry of this thing? And remember that we're talking about this thing as an ongoing thing. It goes on in this direction. We don't necessarily have to say that it goes to infinity. We can extend it. If the page is bigger, we can extend it. Okay, so what kinds of symmetries are there? Well, chemists like to sort of organize the symmetries in terms of certain layers. The simplest is just what's called the point group, which is where we concentrate on sort of the local symmetries of this thing near one of the constituent atoms. So let's say that one there. So we're interested in what kind of symmetries are there that perhaps like fix that particular, say, atom in this configuration. Okay, so there's a number of them. There's first of all 4 rotations, okay, because centered around here, we could rotate, okay, by a quarter turn in that direction. We could also rotate by a quarter turn in that direction. We could rotate by nothing at all, which is also a rotation, or we could rotate by a full half turn, okay, so like all the way around here, which is the same as rotating like that. So there's actually 4 rotations. There are also 4 reflections corresponding to various axes of reflection that pass through the point in question. So there's a horizontal and a vertical axis, so we can reflect the entire arrangement in that line or in that line. Or also these diagonal lines are also acceptable axes of reflections. So altogether 4 rotations, 4 reflections. This makes a group with 8 elements, okay, which is called D4, the dihedral group. But this is such an important group that we're going to give it the simpler name D, and we're going to call it the dihedron group, or the finite dihedron group. Okay, so that's describing local symmetries. Then there are the translation symmetries, okay, and this is the lattice-like aspect, or captures the lattice-like aspect of this configuration. The fact that we can take the entire configuration and say, move it over one atom to the right, or one atom to the left, or one up or one down. Right? Those are all translations. In fact, we can choose any vector that we like. Say from this one here, we could choose, say this point there. We can think about this vector as describing a translation. So we could translate the entire configuration 2 across to the right and 1 up, corresponding to that vector. So such translations are exactly in one-to-one correspondence between vectors in the plane that we can create by, say, starting with that particular distinguished central point and just creating vectors from that point to any other point. Okay, so for example, there's another vector. Whoops, over to that point there. Those are two vectors. Each of them corresponds to a translation. That one there or that one there. And the group structure it's an abelian group, just corresponding to the sum of the vectors. So it's like a vector space, except that it's sort of a vector space over the integers because we're always having to go an integral amount to the left and right. And then there's a larger group where you put these two kinds of symmetries together, where you put the local symmetries and the translation symmetries together, called, say, the space group. Now, mathematically, this is what's called a semi-direct product. It's a kind of a product of the point group and this lattice group, so it's a combination of them. But the way that this product is occurring is a little bit subtle, and I'll have to describe that in a little bit more detail later. So when we put these two groups together, we can, however, expect to get more transformations that we haven't gotten before, like a glide reflection. So for example, if we reflected in this horizontal line here, just reflect that like this, and then moved over by, say, a vector like that, then that's going to have the effect of everything actually moves to a different point, but it's not a translation. So that's a glide reflection. You can also, in fact, have some additional reflections that we haven't thought about before. So for example, if you look at this axis here, okay, that's also a proper axis of reflection, okay, which is, it's like a point group, but it's not centered at a point, okay. And in fact, you could even have axes like this. So you could have an axis coming through like this. Okay, so if you imagine reflecting in that axis, let's say this goes, first of all, reflected like this, and then we could translate it like that. So if we reflect this thing like this and then translate it like that, then it's going to send the entire lattice to itself. So this is quite a rich thing, and describing this space group exactly, describing all the possible transformations is actually a little bit tricky, because you have these point groups, but you have them everywhere. At every point there's a point group, and you have these additional reflections and glide reflections. So it's actually quite a subtle business. So to get at what's going on a little bit more concretely and explicitly, it's useful to try to move towards a matrix formulation of things so that we can draw upon linear algebra ideas. So let's start by looking at this point group as a group of matrices. We're going to call it the dihedron group, and we're going to introduce D equals D4 for the name of this. So this is a very important group. It's a group with 8 elements, okay? And here are the 8 elements. So the group consists of 4 2x2 matrices and their negatives. So plus or minus 1, plus or minus I, plus or minus j, plus or minus k. 1 refers to the identity 2x2 matrix. I refers to this matrix, 0, 1, 1 bar, 0. And I remind you that I'd like to use this alternate notation for negative numbers occasionally. So 1 bar means minus 1. Okay, so that's 0, 1, minus 1, 0, that 2x2 matrix if you like. J is 0, 1, 1, 0. K is 1, 0, 0, 1 bar. And the 4 negatives of these 4 matrices. So that's 8 matrices altogether, and those are closed under matrix multiplication in the 2x2 matrix world. In fact, these 4 here form a very convenient basis of this algebra of dihedrons that I have talked about in my famous math problems lectures, where the 2x2 algebra of matrices is such a fundamental sort of mathematical object that it really deserves more attention, and this is a great sort of starting place to investigate that very rich algebraic structure. So we're going to think about this point group, which is the symmetries of the square, in this matrix fashion. So then we still have to connect it with the geometry of reflections and rotations associated to a square. And interestingly, there's two ways of doing this, because these 2x2 matrices can act on row vectors, so they act on the right on a row vector, or they can act on the left on a column vector. And we get two similar but somewhat different sort of interpretations of these matrices as transformations. So let's have a look at the row vector picture. So here's 2x2 usual world, x-axis, y-axis. And let's start by looking at a general vector x, y in the plane here. What you see here are 8 images of that vector obtained by doing a number of things, by reflecting in the horizontal axis. So then that point or that vector goes to that point there. Or reflection in the vertical axis, in which case this thing here goes to that, this one goes to that. Or reflection in one of these diagonal ones, okay, so that one goes to there, or that one goes to there. Or also you can think in terms of rotation. So a rotation by a quarter turn sends this to this. Rotation by a negative quarter turn sends us there. And rotation by a full half turn sort of reverses things or negates vectors. So explicitly in terms of these matrices, xy is sent to itself by the identity. And if you apply I to it, okay, so you multiply it on the right by the matrix 0, 1, minus 1, 0, you're going to get the vector minus yx, which is this vector here. Okay, so multiplying by I is this quarter rotation in the positive direction, while rotating by minus I would be rotation by a quarter turn in the negative direction. Multiplying by this j, that gives you the reflection in this line y equals x. Multiplying by k is reflection in the x-axis. Okay, so that's a description of how these matrices act on vectors when you think of the vectors as row vectors. If we take the symmetric but alternate point of view that we're thinking about column vectors, so now this is the column vector xy, then we get a very similar picture. We still get an octagon of points, and they're still labeled by the same thing. But the action of these four things is subtly different. J still reflects here to here, k still reflects here to here, but I acts a little bit differently. So if you take xy and you multiply it on the left by the I matrix, okay, you multiply by 0, 1, minus 1, 0, then you get y minus x. Okay, there's y minus x over here, right? Over here we got minus yx. Here we're getting y minus x. So the rotation by I sends you in this direction, while the rotation or multiplication by minus I sends you over here. So this is sort of interesting. It's very simple, but it shows us that we can perhaps think about the group elements as not necessarily transformations at the heart of things. Okay? At the heart of things are these matrices, and the matrices can be interpreted as acting on row vectors or on column vectors, or in fact on quite a lot of other things. You mean these matrices act on a lot of things. For example, they act on 2x2 matrices on the left and on the right. So interpreting these things as transformations of something is something that actually has a lot of flexibility to it. And so when we define something in terms of matrices, somehow we are just appealing directly to the matrix multiplication, and there's the interpretation becomes secondary. Okay, it's a very clean way of thinking about what these groups are. So this is a great chance for me to review some of the earlier discussions and explanations that I've given you about class hypergroups and character hypergroups of a finite group, and indeed the character table of a finite group in the context of this very important example of D4. So here are the elements again, I, j, k, and 1, and of course they're negatives as well. And here is a quick summary of the multiplication properties. So this I squared here, if you square that, you actually get minus 1, or 1 bar. While if you square j and k, then you get exactly 1. So it's almost like quaternions, but a little bit different in that this I element is a little bit different from the j and k, which we've already seen in the previous slide. In terms of the products of things, ij equals k, while ji equals minus k. That's just like quaternions. Ki equals j, and ik equals j. That's also just like quaternions. But this one here is a little bit different. Here, j times k is I bar, or minus I, while kj is I. All right, so this one here is a little bit different from the quaternion story. And now, having understood this group, to understand the character table of it, what we should look at are the conjugacy classes. So that means we should take elements and conjugate them by other elements. That means multiplying, say, on the left by some element x, and on the right by its inverse. Okay, so if y is an element, then we look at x times y times x inverse. That's a conjugate of y. And we want to sort of look at what are all the conjugates of y as we vary x. So with these relations, they're pretty simple, so it's not too hard to work out that there are exactly 5 conjugacy classes. And that, say, the things which are in the conjugacy class of I are only I and its negative. So I together with minus I is a conjugacy class. And j together with j bar, or minus j, is a conjugacy class. And k together with minus k, or k bar, is another conjugacy class. So we have these 3 conjugacy classes consisting of 2 elements. Each one of these 3, and its negative. And then there are the simpler conjugacy classes. There's always just the conjugacy class of the identity. And in this case, minus the identity, or minus 1, is also a class by itself because it commutes with everything just like this does. So there are 5 conjugacy classes. And now if we look at this multiplicative structure that I've told you that Frobenius was actually originally interested in, right? This was Frobenius' original way of thinking about what characters, or irreducible characters, were. So we should ask, what is the multiplicative structure of these conjugacy classes? And we can describe that by this table. So instead of listing equations, here's maybe a more organized way of doing it, just by showing you all the possible products between these 5 conjugacy classes and themselves. So C0 up to C4, C0 down to C4, so we've given these names, C0, C1, C2, C3, C4, let's say. C0 is the identity, so C0 times anything is just going to be the anything, so we just get a repeat of the names here, and similarly in this first column, that's just a repeat of these things. So what is C1 times C1? We're doing multi-set arithmetic here. So these are capital C's. So I want you to think about these as multi-sets. This is a multi-set with 2 elements, has I and I bar. So let's say I multiply this multi-set by this multi-set. What does that mean? Well, I have to perform all possible multiplications between elements here and elements in here, and I have to create a multi-set of all those possible multiplications. So I have to take I times I times I bar times I, and I bar times I bar. Now I times I is minus 1, and so is I bar times I bar. So we're going to get minus 1 twice. We're going to get this conjugacy class twice, 2C0. While I times I bar is the negative of that. The negative of this is C4. So we can get 2 C4s. So the result of C1 times C1 is 2C0 plus 2C4 in multi-set language. And that's the same thing that you get when you multiply C2 times C2 and C3 by C3. However, if you multiply C1 times C2, I times j, well, I times j is k. And I times j bar, well, that's going to be minus k. And I bar times j, again, you get minus k and k. So you're always ending up in the k conjugacy class. So C1 times C2 is always C3. And similarly, C1 times C3 is C2, and C1 times C4, well, that's just going to be C1 because this is negative the identity, and this conjugacy class here is closed under when you multiply it by minus 1. So this is then the complete table. C4 has the property that when you square it, you get C0, and otherwise you get, well, C0 times C4 is C4, C4 times C1 is C1, C2, C3. Okay. So this is a table that describes it's really not a hypergroup, it's the language of fusion rule algebras formed by these conjugacy classes for the dihedron group. Now, I've slowly been trying to convince you that it's actually the probabilistic point of view that has the most advantages, really, in terms of having a nice theory of harmonic analysis and has lots of nice applications to random walks and other things. So to get the hypergroup story from the fusion rule algebra story, remember that we always normalize. What we do is we replace the capital C's with little c's, where we just sort of divide the multisets by whatever is required so that the total weight of that little multiset is 1. So the capital C1 had 2 elements, I and I bar. So to get the little c1, we just take half of that. So half of that multiset. So we're working in the world of rational multisets where we're allowed to have objects with, fractional multiplicities or negative multiplicities. No problem. Okay, so we have little c0 up to little c4 as the elements of the class hypergroup. And here then is the multiplication table that I've just got, but just rewritten. And it's all immediate. The only main difference is what's happening here. Instead of getting 2c0, 2 capital C0 plus 2 capital C4, the total number of coefficients here has to add up to 1 because it's got to be a probability. So it ends up being 1/2 C0 plus 1/2 C4 for the product of C1 with C1. And that's repeated with C2 squared and C3 squared. So that's the class hypergroup. Those are all the structure constants, now all of them, for that class hypergroup. And here's the actual hypergroup. It's an object with 5 elements. And of course it's commutative. Okay? So we've gone from the group. We could write down a group table. Okay? That would also not be hard, but it would be an 8 by 8 table. So we've gone from the 8 by 8 to the 5 by 5 because there are fewer conjugacy classes. It's not a big reduction because this group is pretty close to being commutative to begin with, okay? But if you have a large finite group that's highly non-commutative, then this contraction to the class hypergroup really is a major condensation. It really simplifies or reduces things often dramatically. Okay, so this is the class hypergroup of the point group of our square lattice. Okay, so now the hypergroup character table. Okay, so the hypergroup character table of the hypergroup that we've just been talking about. So that means we want to find out all the ways of assigning numbers to the hypergroup elements, to little c0 up to little c4, so that those numbers satisfy exactly the same relations as the abstract ci's do. So this is a pleasant little exercise, really only involving a little bit of high school algebra, and I'll leave it to you, okay, that there are exactly 5 of these characters. There's the identity character, which there always is, and every character has the value 1 at c0. And these 3 characters here are all sort of similar, okay? And what they do is they assign a value of 1 to one of these 3 and a value of -1 or 1 bar to the other 2, okay? While C4 has the value 1. Remember that C4 squared is C0, and C0 is always 1. So C4 has to always be 1 or minus 1. Okay? So there's 4 cases where it's equal to 1, and 1 case where it's minus 1. So the case where it's minus 1, that forces, you can easily check that these C1, C2, C3 values for that character have to be 0, and so we get this sort of different looking character as part of the character table. So what's the connection between this and the more traditional group character table that, say, a chemist is likely to know about? Well, the group character table is exactly the same as this. For the group character table, we need to multiply this chi4 by 2. So the entries are 2, 0, 0, 0, minus 2. And in fact, you could see that immediately, because if you look at the 2 by 2 representation of the group that I sort of started with as the definition, the identity element has trace 2, and those I, J, K matrices all have trace 0, and the negative identity obviously has trace minus 2. So where this comes from is very clear. So the hypergroup character table is, in some sense, nicer to deal with, and is more symmetrical, and you'll see why. So now that we have this thing here, we can extract some information from this, right? So one of the things that this table allows us to do is to realize the hypergroup in terms of the columns here. So we can think about C2 as being this column vector. We can think of C3 as being this column vector. And then the product of C2 and C3 in the hypergroup is just what you get when you multiply pointwise these two columns. All right, so in this case, if we multiply these two pointwise, what would we get? 1 times 1 is 1, minus 1 times minus 1 is 1, 1 times minus 1 is minus 1, minus 1 times 1 is minus 1, 0 times 0 is 0. So the product of this one and this one is exactly C1. So this gives us a sort of an immediate realization of the hypergroup. But pleasantly, it also gives us a realization of another algebraic object, the dual object, because the rows themselves also have a similar kind of algebraic structure, because we can multiply any two rows pointwise. So for example, if we multiplied chi2 by chi3, what would we get? We get 1, 1, minus 1, minus 1, 1. We'd see that we're getting chi1. And what happens if we say square chi2? We get 1, 1, 1, 1, 1. We're going to get chi0. What if we say multiply chi1 by chi4? We get 1, 0, 0, 0, 1 bar. We're just getting chi4. All of them are quite easy, except for one of them, which is chi4 squared. If we square chi4, we get 1, 0, 0, 0, 1. Can you see how to express that as a linear combination of the rows? There's only one way. The only way of expressing 1, 0, 0, 0, 1 as a linear combination is to take 1/4 of this plus 1/4 of this plus 1/4 of this plus 1/4 of this. In other words, you take the sum of chi0 up to chi3 and divide by 4. Yeah, that's like the average. The average of this is 1. The average of these guys is 0. The average of these is 0. The average of these is 0. The average of these is 1, because we're talking about chi4 squared. So that's pretty interesting. That means we're going to get another kind of hypergroup-like object on the dual side. Of course, that's the character hypergroup of our group. So the character hypergroup of D4 consists of these 5 elements, which are the characters of the hypergroup K of D. And here is the multiplication of this hypergroup here. So it's almost an abelian group in the sense that any two of these multiplied together is another one. So chi1 times chi3 is chi2. chi2 times chi2 is chi0, etc. With the sole exception of this one here, which is what we just computed, that if you multiply chi4 by chi4, you get 1/4 chi0 plus 1/4 chi1 plus 1/4 chi2 plus 1/4 chi3. So this is really interesting, and it's important. Okay, so it's important to think of these two hypergroups as both being sort of equal. They're dual. They're different sides of the same coin. And to clarify that, let me calculate for you the weights of these 5 elements. So let me remind you that the weight was what you get when you multiply an element with its star. Okay, so chi1 always has weight 1. I'll just put the weights over here. Okay, that's weight 1. Chi1, what's its star? Its star is itself, because chi1 times chi1 is chi0. And the coefficient of chi0 is 1. So the reciprocal of 1 is 1. So that also has weight 1, as does this, as does this. What's the weight of chi4? The weight of chi4 is 4, because the star of chi4, like the antiparticle of chi4, is chi4 itself. And the coefficient that chi0 appears in that product is 1/4. And the reciprocal of that 1/4 is 4. Okay, so the total weight of this hypergroup is 1 plus 1 plus 1 plus 1 plus 4, which is 8. That's actually also the same as the weight of the original hypergroup. Do we know what those weights were? Well, the 1 and the -1 had weight 1, and the 3 hypergroup elements corresponding to i's and j's and k's all had weight 2. Because when you take C1 squared, you get 1/2 C0 plus 1/2 C4. Remember that? So the reciprocal of the 1/2 is 2. So the weights of the original hypergroup are 1, 2, 2, 2, and 1, for a total of 8. Here also the total weight is 8. And these numbers actually figure very prominently, and to explain that I'm going to go back to the character table for the hypergroup. All right, so here's our character table for the hypergroup again, and now I'm going to put in the weights that we've just calculated. So that's 1 and that's 1, and I said that these all had weight 2. Okay, and over here the chi's, these guys all had weight 1, while this one has weight 4. And now I can explain some other further aspect of this hypergroup story, which is very important, which is the orthogonality relations. So we're going to talk about this more generally later on, but I just want you to see this in this example. Okay, so having worked out all these things, I can now show you that this character table has orthogonality, but crucially there's 2 kinds of orthogonalities. There's orthogonalities between the rows and also between the columns. So let's look at the orthogonality between the rows. Okay, so I'll say this row and this row. By orthogonality, we usually mean something like a dot product. Say like if these were vectors, the usual dot product would be this times this, plus this times this, plus this times this, plus this times this, plus this times this. If we do that in this case, we get 1 plus 1 plus -1 plus -1 plus 1, which is not 0, which is usually what we think about in terms of orthogonality. But the dot product that is appearing here is a weighted dot product, where you have to weight these various products by exactly these weights which are appearing here. So we have to take this product times 1, that's 1. This product times 2, that's 2. This product times 2, that's -2. This product times 2, which is -2. So we have 1, 2, -2, -2, and this product times 1, which is 1, for a total of 0. Okay, what about, say, the product or the orthogonality between chi3 and chi4? So 1 times 1 times 1. This product is 0, that product is 0, that product is 0 automatically. This product is -1 times 1, we still get 0. So it turns out that these 5 rows are completely orthogonal. Any 2 of them are perpendicular. Their dot product is 0 with this weighted dot product. But miraculously, the columns are also orthogonal. Let's check that. let's say, the dot product between this one and this one. But now we have to use these weights. So this product times 1 plus 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 this product times 4. That's obviously going to be 0. Here, 1 minus 1, 1 minus 1, 1, that dot product is going to be 0. How about between the first and the last columns? So 1 times 1, that gives us a total of 1, plus 1, plus 1, plus 1. So we have a total of 4 so far. And now we have a 1 times a minus 1 times happily 4, which gives us a total of 0. So this is a remarkably beautiful thing, and you should be suitably amazed, okay, and happy to see such a pleasant story emerging, a very beautiful symmetry between the rows and columns, between the original hypergroup, the class hypergroup, and between the character hypergroup. Okay? And the fact that this more or less extends in general is just an incredibly beautiful aspect of this branch of algebra. I'm J Wildberger. Thanks for listening.